Welcome students to the next lecture of microcontrollers. So we will go through the basics of the microcontroller in this lecture. So in the last introductory lecture we discussed briefly about the role of digital logic in describing the different blocks that you might have in a microcontroller, and how in this module we will look into those blocks from a functional point of view rather than focusing on the gate level details of those blocks. And then we also discussed the basic difference between a microprocessor and a microcontroller, and what are the different applications of a microcontroller in our day-to-day life. So today in this lecture we will start gradually with the basics of the microcontrollers. So a basic microcontroller, as you see in this picture, consists of a CPU and different memory blocks, and also IO ports. So you saw that this was the basic difference between a microprocessor and a microcontroller in your last lecture. So in a microcontroller, all the necessary blocks are within the uh, same chip. Okay, so so basically you have the CPU, memory, and IO ports, and then they are connected to each other through different buses: the address bus, the data bus, and the control bus. So just a second, my pen is not working. Actually it is, but what's the problem here? So let's see, and there you have. um, okay, so so yeah, so as I was saying, you have the CPU here, and then you have the memory and the IO ports, and this memory may contain your ROM and the RAM blocks all together, and then you are connected to this memory with the address bus and the data bus. You are also connected to the input output ports with the address bus and the data bus. And you can see that the address bus is bidirectional in nature. Okay, so if you look, the address bus is unidirectional in nature, so it goes from CPU to the different blocks, but your data bus is bidirectional, so you have these arrows on both sides. So this means that you have the exchange of data between the different blocks and the CPU. The control bus also, you see, are bidirectional, so you have exchange of control signals through this control bus between CPU and the different blocks. But the address bus is unidirectional, so the CPU uses the address bus just to locate some addresses in the memory, so that's why the address bus is unidirectional. So let's focus on the CPU first. So CPU is the brain of the microcontroller, so it processes all the information stored in the memory and executes those instructions. So uh, the information in memory will usually consist of two parts, as we shall see. So instruction and data. So there will be some instruction that tells the CPU to perform this and perform that, and then there will be some data where this instruction will be performed on. And then the set of all the possible operations of the CPU can together be called an instruction set. Okay, so such operations, like what are the possible operations in a CPU? So that can be loading data from memory into a register inside the CPU, perform some operations on that data, for example, complement the byte of data, or perform binary operations on the data as well. For example, you can add two numbers together, and so on. And the memory serves two purposes. So basically, it stores the instruction to be carried out by the CPU, and it also stores the data on which you need to perform the instruction. So both of them are stored in the memory, and the memory has two functions. And then the IO ports, they allow the microcontroller to communicate with the outside world. So they could allow the microcontroller to interface with an LCD display, for example, or maybe with some keyboards, so that you can put some instruction, you can input some instruction, or it can be, let's say, any other sensors like an analog to digital converters, or a motor, and so on. So we will see towards the end of this module how you are interfacing different external devices with the microcontroller using the IO ports. And then comes the address bus. So this is used to identify the devices and memories connected to the CPU, and the CPU puts the address on the address bus as a string of bits, and then uh, each device can then find out if the CPU wishes to communicate with it or not. And then, as I said in a couple of slides back, that address bus is unidirectional, which means that the CPU only uses the address bus to send out addresses. Okay. Whereas in case of the data bus, it is bidirectional in nature, and the CPU uses them to both send and receive information. So CPU sends out information to ROM or RAM block. It can also receive some information from that block. And then the processing power of the microcontroller is sometimes related to the size of its data bus. For example, an 8-bit bus can send or receive 1 byte at a time, whereas a 64-bit bus can send or receive 8 bytes at a time, so 8 times faster. So depending on the size of the data bus, you can determine the speed by which the microcontroller can operate. There are other factors that determine the speed as well, but this is one of the main things. And then finally, the control bus, which is used to signal each device whether it is being read or written to by the CPU. So the control bus signals the CPU to tell whether an address is valid or for a given device or not. So there are two functions of the control bus. One is to signal each device um, whether it should read or write uh, from the CPU, and it also tells the CPU whether an address is valid for a given device or not. So let's do an example. A microcontroller has an 8-bit data bus and a 16-bit address bus. Determine the maximum number of memory locations possible and the largest number that can be read into the CPU at a time. So the maximum number of memory locations possible is determined by the address bus. So that will be 2 to the power the address bus width. And in this example, it is 2 to the power 16, which is 65,536. And the maximum number that can be read into the CPU is 2 to the power data bus width minus 1. So if it is an 8-bit data bus, then you can read up to 255. So between 0 to 255. So these are the 256 numbers that you can read, and the maximum is 255. So let's go through the different steps of the read cycle. So when your CPU is trying to read some data from the memory, so the first step is that the CPU places the address of the desired location in memory on the address bus. So where from you you are going to read the data, that should be put in the address bus. Okay, so so then the control bus signals the memory the address on the bus is valid. Okay, so that's the function of the control bus you just saw. One of the function of the control bus is to validate the address, and then the next step is the memory block fetches the data from the particular address that is specified on the address bus and places this on the data bus. Okay, and then the fourth step is then again the control bus signals the CPU that whatever data that has been put on the data bus is valid or not, and finally the CPU takes the data from the data bus. So just a moment. My pen is doing some problem. Okay, so let's proceed. So we saw the read cycle. Now let's go through the write cycle. So here the steps involved are: first, the CPU places the address of the desired location in the memory on the address bus. So this step is the same whether you are trying to read from a location or write to a location. You have to first identify the address. So that is the first step here, and then the control bus signals the memory whether the address is valid or not. So this is again same as the previous step. Then the next step is that the CPU places the data on the data bus. Again, this step is same. The control bus signals the CPU that the data on the data bus is valid. And then finally, the memory block takes the data from the data bus and stores it in at the location specified by the address bus. So here, the data is taken by the memory block and put into the specific address. So here this is the case of writing. So the CPU places the data and the memory takes it. In the previous case where we were doing the read cycle, the memory places the data on the data bus and the CPU takes it. So whichever way the data has to travel, whether it's a read or write, um, that particular aspect changes, but the most other steps are more or less same. So let's do an example. So let's say we have a 8-bit 256 word RAM block with the contents listed as shown below. So a CPU is required to read the memory contents at location 1BH into an internal register A. Okay, so so this is your 1BH. So okay, let me tell you how to read these addresses. So whatever is there on this side, you read from this direction to this direction. Okay, so 0 1 and then wherever is B. Okay, so here is B. Okay, so 0 1 B means this part. Okay, so 0 1 and then B. Okay, So basically we are interested in this data. So this is the address 01B and the data there is AF. So this is a hexadecimal representation. So we have AF. So now we are required to write this data AF into an internal register A of the microcontroller. So explain step by step by use of a flowchart the procedure the CPU must follow to achieve this and give the contents of the register A when all steps have been finished. So this first step is to identify the address, which in our case is 1BH. So that particular address 1BH is put in the address bus. And then the control bus signals the memory that this particular address that is already put in the address bus is valid. And then once that step is confirmed, you have the data AFH that is put on the data bus. So this data was residing in this address, so that is put on the data bus. And then again the control bus signals the CPU that this particular data is valid, and then whatever is the content of the data bus, which is AFH right now, is pushed to your register A, and the final contents of the register A will be this particular number AF, which is in hexadecimal form, and that number in binary is this. So this is the whole operation, and the final contents of the register A will be the data AF. Then now if you want to repeat the same exercise, and now suppose you are asked to move the data in register A to be written back to the location 2CH in memory, then what will be the flowchart of this write cycle process? So let's say again, if you look into the memory, so this AF, which was in 01B, this is the way to read. So this was moved to your internal register A. This was moved to your register A, AFH. This was there, and then this has now to be moved to the location 02C. So this is the location where your AF will finally move to. So now let's go through the flowchart again. So the first thing is to identify the address. So here we are trying to write, and we have to identify the address where we are going to write. So that address is 2CH that has been given in the problem. So that address has to be put in the address bus. And then the next step will be to validate this address. So the control bus will validate the address to the memory, to the CPUs. And then the control bus will validate the address to the memory, and then we will fetch the data, that is AFH, to the data bus. Okay, so this data is moving to the data bus from the register A. Okay, so this data is in your register A right now. Okay, and register A puts this on the data bus. Okay, and then the control bus again validates the CPU that the data on the data bus is valid, and then the data on the data bus, which is your AFH now, that moves to the final memory location 2CH, where you are supposed to write. So that was the example of write cycle. So now let's look further into the details of the CPU. Okay, so all microcontrollers have a CPU which acts as the brain of the device, as we discussed. And let's see what's inside that brain. Okay, so we have different blocks. We have a program counter, we have an instruction register, we have arithmetic and logic unit, we have instruction decoder and control units, and then we have some register arrays. Okay, so we'll go through the functions and the details of each one of them. So let's say to perform certain tasks, the microcontroller must be given a list of step-by-step instructions. So this is called the program. So when you write a program in a high-level language like Java or C, you are basically telling the computer what to do. Okay, so this high-level language, Java or C, is basically converted to a hardware level language. Okay, or a basic instruction level language that the computer can understand. Okay, so that's what the program uh, is doing. Okay, so in a microcontroller, the program consists of a list of instructions that are stored in the memory, and the program counter, which is one of the blocks you saw inside the CPU, points to the address, the next instruction to be executed, which is stored in the instruction register and interpreted by the instruction decoder. So see how the different blocks inside the CPU are working together to get the instructions to be executed. So there is a program which is an interpretation or a translation of the high level language program that you have written, let's say C or Java, that has been translated to a machine level uh, set of instructions that the microcontroller or the CPU can understand, and that is stored as a list of instruction in the memory. Okay, so this is the first part, and then the program counter points to the address, the next instructions to be executed. So program counter first points to the first address where the first line of the program is stored, and then as the program gets executed, the program counter moves and it points to the next address and then to the next, and so on until the program stops executing. And in between, what is happening is that whatever is stored, you know I mean the next instruction to be executed is stored in the memory. Okay, and that instruction, okay, um, has to be interpreted by the instruction decoder. Okay, so so first the instruction has to be valid. Okay, then it has to be executed. Uh, so the set of instruction that can be possible is there in the instruction register, and then that is interpreted by the instruction decoder. So these two things validate the instruction. The instruction has to be valid. The instruction has to be something that the microprocessor can understand. Okay, then only the instruction has to be um, then only the instruction can um, be executed. Okay, so the instruction decoder, as I just said, can be considered like a dictionary. Okay, so it stores what each instruction means and the steps the CPU should take upon receiving each instruction. Okay, so whenever I say something to you, like, okay, um, do this or do that, then first your brain processes that, and then it actually validates it with a set of, let's say, words that is there in your brain. Okay, so let's take the example of the English language. So when I'm saying something to you to do in English, then your brain has a set of words that is stored, which is your vocabulary, and you first match that up with that vocabulary. Okay, and then there is also a dictionary to tell the meaning of uh, that word. Okay, so once it is there in your stored vocabulary, and once you know decode it by the help of this dictionary or the instruction decoder, then only you can execute that instruction. So the same thing happens in case of a microcontroller. Okay, so so the very a very important part of any CPU is also the register array, because these register arrays are used to temporarily store information that's that's the CPU needs to process. So the information could be a value that needs to be processed, or it could be the address of some value needed to be fetched from the memory. And these registers can be 8-bit or 16-bit and so on, depending on the hardware architecture of the microcontroller and the capabilities of the CPU. Next comes the ALU, or the arithmetic and logic unit. So it performs all the arithmetic operations such as addition, subtraction, and logic operations like AND, OR, XOR, etc. And it is controlled by the control unit and receives its data from the register array. So the register array stores the data temporarily, and then it brings that to the arithmetic and logic unit to be processed, like for example addition, subtraction, or any logic operations. So that is how this works. So let's go through the steps of an execution cycle. So let's say you want to execute a program. So during the program execution, the following steps are performed. So first, the contents of the program counter are placed on the address bus. Okay, so the program counter is very important when you are executing a program, because that points to the address where your code or the program is stored. Okay, so let's say your program is stored in your memory. Let's say this is the memory block. Okay, and let's say this is the first instruction of your program, then this is the next instruction of your program, and so on. So let's say i have I have 10 lines of a program, and each line says something or the other to do to the microcontroller, and each of those lines are stored in these addresses of the memory. So this is address 1. Okay, this is address 1, and then this is address 2, and so on. And okay, I can explain this better on the board. Okay, so let me go to the board. So let's say you have my pen is not working. Let me see if I can fix this while I'm online with you. So Okay. Okay, here we are. Let's see if it works. Okay, so let's imagine that this is your part of the memory where your code is stored, and the code has, let's say, 10 lines, 1 2 3 up to 10, and you have um, 10 corresponding memory locations where your 10 lines of the code is stored. Okay, so this is the first line of your code, and this has some address. So let's say address 1. Okay, this is address 2, and so on. Okay, so different lines are stored in different address locations of the memory. Okay, so this is your memory. Okay, so now what your program counter does, this is your program counter. This is a separate register which contains, let's say, the address 1. Okay, so this contains at the beginning the address of the first line of the code. Okay, and then whatever is there in this first line, the CPU reads that, and then the CPU tries to execute this line. Okay, and then it goes to the next line. So now the program counter will contain address 2, and then it will point to this line. Then again, this line will be read and executed, and then the program counter moves to this line, and so on until it reaches the last line of your code and finishes executing the entire code. So going back to the execution cycle, so first the contents of the program counter are placed on the address bus. Why? Because this is the current address where the current line of the program is stored. So that has to be placed on the address bus, and then the read cycle is executed in step 2, placing the instruction operation code into the instruction register. So once this program counter address is placed on the once the program counter address is placed onto the address bus, the read cycle, as you saw previously, there are 5 steps to the read cycle. That cycle is executed, and whatever is the instruction is placed on the current address that is in the address bus. That instruction uh, moves to the instruction register, and then it is decoded and it is executed. So the instruction decoder in the next step reads this code and determines what it should do or what's the next step. So let's take the example of a simple microcontroller. So let us imagine that we have a very basic microcontroller. While real microcontrollers have hundreds of possible instructions, we will start with an instruction set of 4. So what are these instructions? The first one is load. So again, these instructions are given in assembly form and in equivalent hexadecimal form. So this means that this has already been translated from a high level language like C or Java. So you have written your code in, let's say, C, and then that particular instruction in C is translated into an assembly form that is understood by the machine, or that is understood by the microcontroller. So you will see that these instructions are in assembly form. You haven't seen any such instruction while you learned, let's say, C or Java or Python, let's say. So these are in assembly form. So this means LDA means load the register A with some data. Okay. INCA means increment the register A. Whatever the value in register A, you increment that. Then DCA is decrement the value in register A, and JP with some address means jump to this particular address location. Okay, and you can see that each of this assembly language instruction has an equivalent hex form. Okay, so this is what is stored in the memory of the microcontroller. So load A, there is an equivalent hex code to load A, which is 3E. Okay, so 3E followed by whatever is the data is stored in your memory. Okay, and then for increment A you have equivalent hex equivalent of E4. For decrement you have E5. For jump you have D6 with this address. So, and the equivalent operations for this is basically load the register A with the data, as I said. Increment A means add 1 to the content of A. Decrement A means subtract 1 to the content of A. And jump to a particular address means you are loading the program counter with that address. So we will get to the details of that later, what exactly it means. And then each of these instruction has some size. So this is a 2-byte instruction because your load A, the instruction itself is 1 byte because it is denoted by 3E, which is 1 byte of data, and the data which will be loaded is another 1 byte. Okay, so therefore it is 2 bytes of instruction because this instruction always comes with a data to be loaded. Then these are 1 byte instruction, increment and decrement, because there is no data accompanied. It just increments whatever is stored in A and it decrements whatever is stored in A. So these are 1 byte instructions. And then this is a 3 byte instruction because D6, which is the hex equivalent of the jump, is 1 byte, and the address where it will be jumping is 2 bytes. Okay, so that's why it's a 3 byte instruction. So now you note that how each of the instruction has more than one part, and they are of the form opcode and operand. So in case of your load A, this is the opcode and this is the operand. The data on which you are executing this instruction is your operand. Okay, and the instruction itself is called opcode. So the opcode part, which is load A, this tells the CPU which operation to perform, and the operand, which is the data, this tells the CPU which data to perform the operation on. Okay, so some instruction will be having opcode and operand. Some instruction, as you saw, just comes with the opcode. So for example, increment A and decrement A. Okay, so note that in English form, the opcode indicates the meaning of the instruction. So in this example, LD stands for load. Okay, so so as humans, it is much easier for us to read the instruction in assembly form rather than in machine code form. Of course, the microcontroller stores each instruction in memory in binary code. For example, INC is stored as E4, which is a hex, and E4 in binary form is this particular string of numbers 11 10 01 00. So there is a unique binary code representing the opcode of each instruction, and this is known as machine code. Okay, so this is what I was trying to say. So whenever you write a program in a high level language, C or Java, that has to be translated to a machine level code for the machine to understand. The machine only understand ones and zeros and different combinations of them. So increment, let's say in C you might write this, let's say x is a variable, and then you write x plus plus, which means incrementing this number, okay. Or you might also write x equal to x plus 1 in a high level language. So this is translated to INCA, okay. um, let's say we take a here, okay. So a plus plus means increment, or a equal to a plus 1 also means increment in a high level language. This is translated to INCA in assembly language, and further this INCA represents nothing but a string of numbers which is denoted by E4 in hexadecimal format, or 1 1 1 0 0 1 0 0 in binary. And this is the final thing that is stored in the memory, and the CPU reads these and figures out using the instruction decoder what it has to do, okay. So let us look at a simple assembly language program for our basic microcontroller. So let's say we have load A with 05. So we have to load 05, which is in hexadecimal format because of this H, okay. So we have to load 05 hex into register A, and then we have to increment A 3 times, sorry, increment A 2 times, and then decrement A, and then jump to the 16-bit memory location 000 hex, 0 hex. So what does this code do? The code loads 05 hex into the A register, increments A by 1, increments A by 1 again, decrements A by 1, then jumps to the first location in memory. That is the start of the program. It does this by loading the program counter with 0000 hex. Okay. So let us look at the memory for the above program. So the first location in memory holds the hex value 3EH. So this corresponds to the machine code form of the load A. So now notice how the memory is organized when you are having a code to run. The first line of the code starts from the memory location 0000. So we have to read from this side to this side, as I said. So 0000, the first location of the memory um, is now containing the first line of the code. So as I was saying, so the first address, when I was drawing this analogy, so the first line of the code is written in the first address of the memory, and then as the code proceeds from the first line to the end line, your program counter keeps incrementing by one address to the other, okay. So first it contains the address 1, and then it goes to address 2, and so on, okay. So so moving back to the program that we were discussing, so here as you see, the first line of the code, which is load A, is stored. So the first line of the code is stored in the first memory address, which is load A, and then the next memory address contains the data, okay, so which is immediately following the opcode. So this is the operand, okay. So the first remember the first line is load sorry, so the first line is load A, with the data 05 hex. That was the first line. Okay, so the load A has an op, this is the opcode, so this has an hex equivalent 3E. So 3E is in the first memory location here, and in the next memory location you have the next data that just follows the instruction load A. Okay, so since load A, as you saw, is a 2-byte instruction, so the first 2 bytes of this instruction are 3E and 05, and those two are stored in the first 2 memory locations. Then the next step was, as you recall, was incrementing A, and incrementing A, INC A, has an opcode that is in hex equivalent form is E4. Okay, so this is E4, and E4 is stored here, and this is a 1-byte instruction, so only E4 by itself, so that is in the second memory location, or memory location 2. Then the next one is again increment, so that is E4 again, so that comes in the next memory location. Then the next instruction was decrement, which is equivalent to E5, so that comes in the next location of the memory. And then finally we have the next instruction, which is jump, and the equivalent hex of jump was D6, so that comes in the next memory location, and that D6 follows by an address, a 16-bit address, so the 2 bytes of that are 0000, and that is in the next 2 memory location, and together this is a 3-byte instruction. As you recall, jump is a 3-byte instruction, as you saw here in this slide. So these 3 bytes are the opcode of jump, which is D6, and the operand, which is a 16-bit address given by 0000. So these are the next 2 bytes. So what I just said is summarized in this slide, and and this is the final memory the organization of this program. And one thing to note, in this microcontroller that we are studying, the example microcontroller with 4 instruction sets, this is basically an example of a von Neumann architecture. So in a von Neumann architecture, the instructions and the data are kept in the same memory space. So you see, this one was your instruction of load A, and whatever you are loading, the data is this, and both of them are stored in the same memory location. So this is called both of them are stored in the same memory space, and this is called von Neumann architecture. Another method of building CPUs is known as Harvard architecture, and this keeps the data and the instructions separate. So again, some instruction take up 2 bytes of memory, which I just explained, whereas other instruction take just 1 byte. For example, increment, and then jump uses 3 bytes. So 1 byte for the opcode, and then the 2 bytes for the 16-bit memory address that it locates to. So now let us add another instruction to our instruction set. Okay, so we started with an imaginary microcontroller that has only 4 instructions, so jump, load A, increment, and decrement. So now let us add another one, which is called JPZ. So JPZ means you jump to the address that is specified by JPZ if your register A is equal to 0. Otherwise you continue with the next instruction. So if your A register is 0, then you jump to the specific address that is that is denoted by this. Okay, otherwise if it is not 0, then you increment your program counter by 3, because you need to increment it by 3 to reach the next instruction, because this particular instruction is itself 3 bytes. Okay, and the next instruction will be occurring at an address which is 3 memory locations apart, and therefore to jump to the next instruction the program counter has to increment 3 places. So that's what I just explained. So when jumping to the next instruction, why is 3 added to the program counter? And the reason is this instruction itself is 3 bytes, and if you are jumping to the address specified by this instruction, which is fulfilled by this condition a equal to 0, then you go to that address and your program counter is loaded with that address. Otherwise you perform the next instruction, which is residing 3 memory locations apart, because this instruction itself is 3 bytes. So in that case you increment the program counter by 3. So now we include this new instruction in another assembly language program. So let's say we have a program where where we have let's come to this org letter. So let's say we have to load the register A with this number, then decrement it, and then we jump, if it is 0, to this particular memory address, and then we have another jump here which is unconditional jump to this particular location 0132 hex. And this org instruction means that the memory that is starting the program, the memory address that is starting the program is given by this. Okay, so this is an assembler directive. This tells the assembler to store the program in memory that is starting at this particular address given here. So org0130h means that it tells the assembler that the memory location that the starting address will have, or the starting location, or let's say this is my address 1. So org0130 means that this address is 0130. Okay, and then your program counter will also be initialized with this address. Okay, and then as and when this program proceeds, your program counter will get incremented to different values starting from 0130. Okay, so let's do an example. Show the contents of the microcontroller memory for the program given in listing 2.2. So you saw the program, which is again repeated here for your convenience. And if you recall the instruction set for this particular example basic microcontroller, so for load A you have 3E, and then comes whatever data you are loading, then increment A, decrement A, all of them have some hex equivalent, E4, E6. Then for jump you have D6, and for jump 0 you have D7. So with this I can write at this table. So therefore, let's say your assembler directive org was saying that your program is starting from 0130. Okay, so this is the first line of your code. So load A 03H is the first line. So in the first memory location you will have 3E, which is the hex equivalent of load A, and then in the next memory location 0131 you have the actual data which is to be loaded. So this is a 2-byte instruction, and the first 2 bytes of this instruction are stored at 0130 and 0131, because your assembler directive says that your program has to be started from 0130. So 0130 is a location or address of a location in the memory that is 8-bit. So that 8-bit is this 3E, equivalent to load A, and the next 8-bit, which is pointed by 0131, is storing the 8-bit data which is to be loaded. Then the next 8-bit 0132 location will have E5, which is the next line of the code, that is decrement A. Then comes the next line of the code, which is JPZ, or jump on 0 to this particular location. So the opcode for JPZ is D7, so that is stored in the next location, and then the remaining 2 location stores the operand, and in this case the operand is a 16-bit address 0130. And note how it is loaded. The 01 comes here, and then comes the 30. Okay, so first the LSBs are stored, and then the MSBs are stored of this particular address. And then the next instruction is jump. The opcode is D6 for this jump, so that comes in the next memory location. And then the operand is 0132, so that is loaded in the next 2 locations like this. Okay, so note how the opcode is loaded first and then the operand, and if the operand is 8-bit data, then it's a different thing. If the operand is a 16-bit address, then it is loaded in a particular fashion. And then you see that whenever you have a 2-byte instruction like load A followed by the data, then you take 2 memory locations to completely write this instruction. Then for an 1-byte instruction decrement A, you take 1 location, and then for a 3-byte instruction like JPZ, you take the 3 memory locations together, and then again for another 3-byte instruction you take 3 locations together. Okay, so now let's say if I give you an example to draw a table detailing the memory address and the program code that would be stored in memory for each line of the following assembly program, then you should be able to do it. Okay, so again this will start from the location 0010, since org is directing the assembler to do so. So, and then each opcode and operand after this will be stored in consecutive locations in the memory. Okay, so so let's say your first location is 0010, because this is what is denoted by this line. And then you have basically 2 instructions. One is load A with 13H. So load A has this particular opcode, and the operand is 13. Okay, so this is a 2-byte instruction, and the 2 memory locations are loaded with this. Then comes the next instruction, which is your jump, and this is a 3-byte instruction, so therefore the next 3 bytes in the memory are loaded with these different parts of this instruction. First part is the opcode itself, which is D6, and then the operand 0012, and then see how the LSB is loaded first and then the MSB. Okay, so now if I ask you to do this as an exercise, so let's say these are my assembly instructions, and you have to find out the locations of the memory where these will be written. So let's go through the assembly instruction first. So org0f02 tells you that this particular address is the first line of your code. Okay, so the first line should start from 0f02. So this is the first starting address, and in the starting address you will have load A. So the opcode equivalent to load A is 3, which is here, and then the next uh, location in the memory will be 0f03, and that will contain the data. Okay, so this XX will be your 01, okay, hex. And then comes decrement A. So the decrement A will be in 0f04, and whatever is the opcode to decrement A, that will come here. So your YY will be, I think, E4 or E5. I think decrement A is, let's look up, decrement A is E5. Okay, so here it will be E5, and then the jump comes. So jump will be in 0f05 D7, which is equivalent to JPZ, and then your LSB comes here already, and this MSB will be 00, so ZZ will be 00 here, and this will be 0f06 and 0f07. So this is how you should proceed this type of problem. So this is your final, this is your final answer. Okay, so I will stop here. I'm sorry for all those disruptions that happened in this lecture because of my pen not working and other software glitches. So go through this video lecture, and I will see you in the next lecture. And if you have any difficulties understanding because of these disruptions and because of some mistakes that I made, we will take up your doubts in the live interactive session. Okay, so I'll stop here. Thank you. Here